Hello and welcome back. This video is meant to provide a supplementary resource to your reading notes for fluid dynamics. Fluid dynamics is found in Chapter 11 of your Etkina College Physics online textbook. Hopefully you have been engaged with getting your notes from the textbook source up to this point. So hopefully this video will help fill in the gaps of what you've already done. Let's begin. Section 11.1, Fluids Moving Across Surfaces, Qualitative Analysis. State Bernoulli's Principle. Well, Bernoulli's Principle in a nutshell basically says that as the pressure of the fluid exerts is going to decrease as the speed increases. So in other words, pressure is going to be less when the speed is greater. Pressure is going to be less when the fluid speed is greater, and there's going to be higher pressure when the speed is lower. Section 11.2, what is flow rate? Well, flow rate is defined, it's also referred to as volume flow rate. It's the volume of the fluid that is passing a particular cross-section of the pipe every second. So we can state that by looking at volume flow rate. The symbol for flow rate is just going to, we'll just say FR. It's the volume per unit time, right? But if we write volume in terms of area times height, height divided by time is speed. So we can write it two ways. Volume over time, cross-sectional area times speed. Okay, now flow rate is going to be in cubic meters per second. Time is in seconds, meters still in meters per second, volume is still in cubic meters, and area is still in square meters. So state the principle of continuity. Okay, I have a diagram here to assist you. Go ahead and sketch it. The principle of continuity states that the volume flow rate is constant throughout a fluid. Okay, now what this means in terms of equation is, well, if the volume flow rate is this, it's going to be either volume 1 over time 1 equals volume 2 over time 2, but that's not really very helpful because what's actually changing in a fluid is not the volume, really. It's the cross-sectional area of the pipe, right? You get from wider pipes and skinnier pipes. So that's going to affect fluid speed. So this version of the equation is much simpler, okay? In other words, the flow rate remains constant, so area times velocity equals area times velocity. Okay, now, what this is going to mean is smaller velocity. Now, area times velocity are inversely related. So what that means, any regions that have wider areas are going to have slower fluid speeds. Any regions that are narrower, okay, so this would be wider, this would be narrow, are going to have very fast fluid speeds. Okay, so the equation of continuity, right, is used to relate the cross-sectional area and the average fluid speed in different parts of a rigid vessel containing an incompressible fluid. So what it's actually demonstrating is the law of conservation of mass. Now use the continuity equation to explain why this happens. When you put your finger over the end of a hose, the water sprays farther. Well, it's spraying farther because the water is moving faster, right? That's a projectile motion concept, right? So remember, an object goes farther if its horizontal speed is greater. Now, how is the speed greater? Well, you put your finger over the opening, you decrease the area, which increases the fluid speed. increase the fluid speed, you're going to go farther. The spray goes farther. Use continuity to explain why this happens. A river has rapids where the river is shallow. Okay, well, when you're in that part of the river where the river's shallow, the cross-sectional area is lower, right? Which means since the volume flow rate remains the same, the fluid speed of those river rapids will be faster. Section 11.3, causes and types of fluid flow. Draw a diagram representing streamlined flow. Diagram the situation represent turbulent flow. Okay, you can sketch these yourself, but streamlined flow, essentially you can see the flow of the fluid is very, very, as the name streamline would suggest, uninterrupted. It just keeps going. Okay, now turbulent flow, on the other hand, the flow encounters, right? Turbulence is this essentially disruption to the flow and kind of a resistance to the flow. And it creates, as you can see, these little tiny areas called eddies, which represent a lot of resistance to that flow. Give some examples of turbulent flow in ordinary life. Well, besides turbulence in an airplane that we experience when the airplane starts to shake when you encounter those types of things, but there's other examples as well. For instance, you get eddy currents that form in shallow river rapids, right? Turbulent airflow also occurs when the air does not flow in a stream-like manner over and around an object. So, for instance, if you had, let's say you had a truck. I'm just going to use a truck as an example. Okay, so you've got a truck. Here's and I'm talking about one of those big rig trucks, okay? And it is pulling a big old trailer behind it like this, okay? Now, the air is going to flow over and boom, up against that thing is going to form little eddy currents right there to the turbulence. It's not very streamlined. That messes with the fuel efficiency of the truck, right? So that would be an example of turbulent airflow over a truck that's designed like this. Well, many trucks you'll see on the road, many of these little freight trucks, have a little dome put on top of the cab right here that allows the air to flow really nice and streamlined over the top. That basically increases the fuel efficiency of the truck by about 10% because it's encountering less resistance. Section 11.4, Bernoulli's equation. Okay, Bernoulli's equation is essentially a statement of conservation of energy with fluid flow. Okay, let me explain. So conservation of energy stated that total energy initial equals total energy final. And we usually came out with an equation like kinetic energy plus potential energy, right? K plus U equals K plus U. That's pretty much what we came out with, which means if you really simplified it, we would get stuff like 1/2 mv squared initial plus m gh initial equals 1/2 mv squared final plus mgh final. Well, remember, we're talking about a fluid here, so we're not talking about the mass of the fluid per se, we're talking about the density of the fluid. So if we talk about the mass per unit volume, then we're looking at the density of the fluid. And you see where that part comes from. Now, the only other difference in there, like I said, this is conservation energy with regard to fluid flow, because you're also interacting with the pressure at two different points. Okay. To finish this off, okay, step 1, you're going to sketch a situation including the upward pointing y coordinate axis, choosing origin for the axis, You're going to choose a point 1 and point 2, okay? Then what you're going to do is identify any assumptions you're going to make. For instance, are we dealing with friction? Are we open to the atmosphere? Do we have atmospheric pressure or not? Constructing a Bernoulli's bar chart will also be very helpful. Okay, then you're going to sketch out part of the chart that will help you with the equation. Okay, and then you're going to start canceling out and zeroing parts of the equation. And then finally, you can go ahead and solve the equation for any unknown variables. Well, that concludes our video for fluid dynamics. It was meant to be short, as you were supposed to get many of your notes from the textbook source itself. I hope you found this supplement to be helpful. Thank you. See you next time.